And yeah, I'm just super happy to be here and present my work. And yeah, I'll get into it because there are many things I want to talk about. But please do stop me and let's say with questions. I love having an interactive talk. And I'm used to, actually, especially if it's something that you see that you really don't like and you have some comments or remarks or questions or doubts, etc. Okay, so I want to talk about practical sample efficient Bayesian inference for models with and without likelihoods. And well, there are a few things I would like to touch in this talk. Well, we'll see them in a bit, but let's start, with some. So why do we want to do this? So the goal is to do Bayesian inference with expensive black box statistical models. This is a kind of a big sentence, and I'm going to unpack it to see, what we mean by it. By statistical model, for the moment, I mean that we do have a likelihood, so we can express the probability of the data given some model parameters. We assume that we have a model, and the parameters live in some space here. It's a black box, though, which means that we don't have detailed information. For example, we don't have the gradient, but say we don't know much about the model itself. Someone gave it to us. It's expensive in the sense that maybe we can take 5 of the order, maybe up to 1,000 likelihood evaluations, but not many more. And we want to do Bayesian inference, which you may be familiar with, I presume. But let's say, just as a quick recap, yeah, we want to be able to compute a posterior, given a prior likelihood. And also, we might be interested in computing this integral here, which is the model evidence. Why do we want to do it? I presume I don't have to really explain a lot about Bayesian inference to this crowd, but just quickly, why do we want to do it? Well, getting a posterior is nice because in the sciences, in engineering, you can do uncertainty quantification through the posterior distribution. You can use the posterior distribution to perform optimal experiment design, to sample the parameters that you're uncertain about. It's useful for robustness. Instead of having a single solution, you have like a posterior distribution of solutions that you can use, and they tend to be, say, to produce more robust solutions. And I think a posterior is also more interpretable because you can look at the posterior and see how parameters of your model interact with each other. And having the marginal likelihood can be useful for hyperparameter tuning. You want to essentially, for example, increase the marginal likelihood of your model. Or model selection, you have several different models. You can pick the model with the highest marginal likelihood. And also one thing that people often forget, but it's very useful, that if you do Bayesian inference, you have a posterior, you marginalize over the posterior, you actually get better predictions in general. As an example, let's say that we might use in a computational neuroscience. I'm not going to explain in detail this model. What we get is that we are showing to some, for example, to a human or an animal, a Gabor patch, which is this oriented grating here. The model does a lot of things. Let's say you can imagine this black box simulating things that happen in the brain. I'm not going to explain, but say what it spits out is, for example, the defiant rate of a neuron in the primary visual cortex of a rat, which is being recorded. So this is kind of like a black box. Stuff happens, but you have this input here and you have this output, which is this this number of spikes that you get from a neuron. Okay, this is an example of a model that we might be interested in, and it might be hard. Let's say kind of checks the boxes that I mentioned before of being expensive, etc., etc. So okay, well, that's our goal. How do we do it? There are, of course, a lot of methods to do Bayesian inference and approximate Bayesian inference, MCMC, Bayesian inference. But the problem with most of these methods is that they require a lot of function evaluations, of likelihood evaluations of the order of thousands, hundreds of thousands sometimes. Or, if they're more efficient, it's because they have more knowledge of the model. So maybe you have the gradients that help you. You have a detailed structure of the model that you can exploit to perform inference in a more efficient way. If you don't have those, then it's tough. So how do we go about it? Well, a sketch solution is that you could use, which is kind of like a standard sketch solution that you can use in this cases. You can fit us, instead of using the original model, you can fit a surrogate model to your likelihood evaluations, and you can form approximate inference with this surrogate model instead of using the original model. And the idea is that the surrogate model is less expensive. And then you can use active sampling to evaluate the landscape in a way that allows you to build a better surrogate model. And so what we need is an approximate inference framework, a surrogate model, and a method idea to somehow combine the two in a contiguous and synergistic way. And so as a method for approximate inference, we're going to use the variational inference. As a surrogate model, you might have heard of them, the Gaussian processes, and as a method to combine the two, Bayesian quadrature. And I'm going to explain very briefly now, just as a sketchy way, the background tools that we're going to use. So a variational inference, we have a posterior, but instead of using the posterior, we want to approximate it with a family of distributions which are simpler in some way. And we do that by minimizing this discrepancy, say this measure of distance, not exactly, between two distributions, Q and P. It is a KL divergence, which is very much used in machine learning. And so what you obtain at the end is an approximate posterior, Q, parameterized by this phi and of theta. And also we get for free, essentially, a lower bound to the log marginal likelihood, which is called the elbow. Essentially, so we get both a posterior and an approximation to the marginal likelihood, which is nice to have. And the nice thing to note is that variational inference casts Bayesian inference now into a problem of optimizing this elbow and integrating away, because we say inside the KL divergence, there is an integral that we need to solve. So just an example, suppose here, this is the target density on the left, and on the right, I'm showing the log density, minus log density. So this is not quite a Gaussian, as you can see. I can still approximate it with a Gaussian, and that's what you get with the Bayesian inference. Voila. But we are not. So when people think about Bayesian inference, usually think about Gaussians. But let's say you can use anything you want. You can use a mixture of Gaussians, and you can get a slightly better result. Here with 2 components. But, we're not limited to 2 components. We use 5 components, and you can see here. Now with 5 components, we get a fairly good approximation of these underlying distributions. So, mixture of Gaussians actually works pretty well. Gaussian processes, the other thing that we use. So Gaussian processes, you can think of them as distributions over functions, and with different parameters. So you can essentially tune to have different samples from this distribution over functions. And so here, what I'm plotting in each panel is draws from a Gaussian process. Each one is a function. Each draw is a function, as you can see here. And what I'm plotting is, for example, these draws from a GP for different values, these underlying parameters, hyperparameters of the GP. So here is a function that fairly fast. So it's while here, so they have short length scale. Here, a function that changes slowly. They have a long length scale. Here, for example, I'm changing the mean function of the GP, so assuming as a quadratic mean. So you can see that there's a quadratic shape underlying, and these functions, as quadratic-ish. But the good thing about, so these are, say, draws from the prior distribution of the GP, but the good thing about GPs is that essentially what you can do is you can observe a few points of a function and then condition on these points, see which posterior GP you would get. And in this specific case, for example, in each panel, we observe always the same 3 points, this one, and this one, okay? And these are the same 3 points, but let's say what's changing in each panel is, as I mentioned, the hyperparameters of the GP. So in this case, we have a short length scale. So by fixing the function goes to these points, and as you can see, so these samples of the posterior now some kind of force to go to these points. There's some variability farther away from the points. If you have a longer length scale, then essentially, yes, you can see this thing here, and essentially their force goes to you have more like a spaghetti kind of thing. And again, with the quadratic function, you get some different posterior. And the GPs are very nice because you can compute things analytically, but I said they also allow you to get uncertainty over the posteriors over distributions, which is useful again to do, say, active learning. And finally, this is kind of just a very high level. Bayesian quadrature is a technique to evaluate integrals when you have a black box function that again you want to perform an integral. And this is kind of integral in which you want to compute z, which is the integral of a probability distribution times this function we want to integrate over some space. And if, say, this P density here is Gaussian, and this f is approximated by a GP with some properties, then the magic of Bayesian quadrature is that you can actually compute this integral analytically, and you actually compute not only the posterior mean of the integral, but also say the variance of the integral. You get a nice, essentially, Gaussian distribution of Gaussian posterior over the value of z, and you can also compute the gradients and everything you want. So everything is very nice. So putting all these 3 elements together, so first of all, we have variational inference. So sorry about that is kind of the only equation I have, I think, it's a complex equation I have. So this is the expression for the elbow, this evidence lower bound that I mentioned, which is used in the variational inference. It's made of 2 parts. We want to maximize the elbow, remember, to get the approximate distribution to be as close as possible to the true posterior. So in order to do that, there are 2 components. On the right side here is the entropy of the variational posterior. So you want to be maximum entropy as possible. And on the other hand here, was the integral of this part here in the log is the log joint, so the likelihood times the prior. Okay? And what you have here is the variational posterior. So it's the expected log joint there. And in Bayesian quadrature, I'm just copy pasting from the previous slides, this integral here. So if you look long enough at these two equations, you notice that they have similarities. In particular, I'm using color to spot them. So we can actually use the Bayesian quadrature to compute this integral here, because say the Q of phi that I mentioned before is a posterior distribution we decide is the approximation we're using. So if we use a mixture of Gaussians, this is a mixture of Gaussians, so it's a Gaussian. I mean, it's a sum of different Gaussians. And this part here, we can approximate with the GP. So if we do that, then we can actually compute the integral analytically. So by combining these two elements, essentially Bayesian inference, Bayesian quadrature, we get to this algorithm, with some other stuff. But essentially, at the core of this algorithm is the combination of these two elements to produce what I called variational Bayesian Monte Carlo. And that's what I'm going to talk about in a second. Sorry, any questions so far? Otherwise, I'll keep going. I went a bit fast over this because I assume that many of you have seen some of this stuff. But I say, if something isn't clear, please ask. I can go back and be a bit slower.
Luigi, does the GP basically act as a smoothing function, or like does the kernel choice and so on also matter in this setting?
So for this to work at the moment, there are extensions, but at the moment, you're kind of forced to choose a Gaussian or exponential quadratic kernel. So it tends to be smooth. Although there are, say, that's something I might mention later. But I say, so yeah, so essentially it's kind of interpolating between the points in a relatively smooth way. But I say if you pick a very, for example, a very short length scale like here, so this is short. This is short, but not that short. If you pick a much shorter length scale, you can have a function that changes much fast. It's still smooth locally, so because it's still an exponential, but still, it's it can change quite fast. So it's still quite flexible. Okay, so how VPMC works? The core of the algorithm is actually quite simple. Then, of course, the devil is in details. But let's say you can imagine it works. Say this is the simplified version. Is that at each iteration, what you do is you sample new points. While at the beginning, you probably draw them randomly or according to some prior. But I say after the first points, at the next iteration, you actively sample them in a smart way by choosing points that somehow give information that you lack. Let's say where, for example, essentially to improve your knowledge of the elbow and to essentially get a better approximation of the true posterior. Then what you do is you train a GP model of the log joint with all the likelihood evaluations you have so far, and then you update your operational posterior by optimizing the elbow to somehow fill in these approximate, say, using the GP to approximate the true posterior. And then you can kind of keep looping until you reach some convergence criterion. This is much simpler by showing you a demo. And this has been published at the New Rips in 2018. Then I have another workshop later. And yeah, a demo will make it much clearer. So suppose these are target density in 2D, like a banana-shaped distribution you can see here. In the central panel, I'm going to show you the points and that VPMC samples in the 2D space. So these are the evaluations that are done of the assumedly expensive likelihood. What's important here is the model evidence. The true model evidence, in this specific case, we can compute it exactly, numerically. But in general, you wouldn't know. So I'm going to plot, let's say, this true value, which is this one, and then the elbow computed by the algorithm. Okay, so I start, the initialization is kind of random, so let's say, don't give it too much weight. So these are what I'm showing here, these are the two, it starts with two components. So these are the two mixture components of this mixture of Gaussians as an approximate posterior. And then, it starts going. These new points here are sampled in purple. At the beginning, let's say, it's kind of trying to fill in the space a little bit. And then essentially, I'm kind of skipping on some details, but I say what happens next is that, okay, once the algorithm has been stabilized, it will start throwing in more and more components until the elbow stabilizes. So I say now there are 3 components, and it kind of samples here at the borders. Now you can see it's kind of extending here and here. It's kind of, and it's filling in the probability posterior mass where it's needed. And there you go. So let's say, so now it has, I think, about 10, 12 components, or maybe more, 15. And and it has sampled the points, say, not randomly, but let's say in a smart way to fill in where the algorithm thinks, let's say, there is posterior probability mass to be discovered. And as you can see from the model evidence, it started, kind of uncertain, and then it starts going up and kind of converging close to true value, which we don't know. Say we know in this case, normally you wouldn't know, and the argument will stop at some point thinking that it has converged. Then we can discuss how to check that it actually converges. And the result is that it works in practice. I'm not asking you to look at these graphs, but say you can check, we checked on synthetic and real problems, and it works well. The only important thing to see in all these graphs essentially is that the black curve is kind of below, or say consistently below the others, except in a few points, but it performs fairly well in those scenarios. And this is an example of posterior that you can get. So just to show that it works, not just with 2 dimensions, let's say you want to work, in 6, 7, 10 dimensions. And it does a decent job. So what I'm showing here is a marginal posteriors, say the one-dimensional marginal posterior and the pairwise posteriors for various parameters of the models I mentioned at the beginning, of the neuronal model I mentioned at the beginning. It doesn't really matter for this talk what these parameters are. I say what I just want to show you that, first of all, the parameters are not, say the posterior are not necessarily Gaussian. As you can see, there are deviations, say even strong deviation from Gaussianity. And the model, say this method is able to capture those. And here in this panel, I'm showing the true posterior got through expensive MCMC. And here, what we got for, say, one run of VPMC, not even the best run, just a random run from VPMC, after 53 iterations, which corresponds to 260 evaluations. So by comparison, to get this here, you need tens of thousands of evaluation of your likelihood. While here, we got away with only 260. Of course, there are some deviations, so it's not perfect. It's an approximation, but I'd say for if you think in terms of the computational cost, there is a factor maybe of 50 or 100 between these 2 graphs. So let's say, then maybe you can decide to refine this approximation later, but I'd say still it's much cheaper. Okay, so I want to get to the limitations of the approach, because of course there are limitations. In this original, first of all, let's say one big thing. So if you were paying attention, the title of this talk is models with and without likelihoods. But I'll say one assumption that I mentioned early on is that we need to have the likelihood for using it. So and as you probably know in this crowd, let's say there are lots of cases in which you don't have the likelihood. So how do we do with that? And then say there are other, let's say something that emerged before that was asked by Suyog. So he mentioned that so is it smooth? And so this method works when the posterior is relatively smooth. And I say also not too complex. Let's say, it's kind of hard to quantify what you mean by complexity, but let's say, so definitely there are lots of cases in which, let's say, if you posterior has some mildly pathological scenario, let's say this method won't capture it. Essentially, this method can capture stuff that you can model with your GP. And, say, so if your posterior has some difficult part of the space which cannot be modeled well by a GP, then it won't work. And similarly, so even if it can be modeled by GP, but let's say, there are, for example, different modes, that's kind of hard to capture. This method might capture it, but let's say, but it's our kind of open problems. Even with the MCMC, if you have different modes which are very well separated, it's a hard problem. Again, another major problem, let's say you can think of it, is that it only works for relatively low dimensional problems up to, let's say, order of 10 dimensions. And again, this has to do with using a GP to approximate posterior. And finally, again, because we're using GPs, GPs become very fast, expensive as you increase the number of evaluations. So this is nothing to do with the data that you have, but say just specifically with the number of likelihood evaluation you make. So the more points you're covering in the space, the more expensive the GP will become. And such that essentially you can probably get up to of the order 1,000 evaluation, and then the GP will become the main cost of whatever you do. I would like to cover, attack these things, but say the first thing I wanted to cover is, okay, so what happens if we don't have a likelihood? Because this is, a very common situation, especially, in the kind of fields in computational biology, computational neuroscience, in which I work, sometimes you don't have the likelihood. So I want to talk briefly about this technique. So you might have heard of Symmetrybased inference, also because it's one of the, kind of major projects of the CI. So CI. And so if you don't have the likelihood, by say you're able to simulate data from your model, so let's say you can sample from your model given some parameters, so you can generate data, then there are several ways to do a simulator-based inference. One very famous one is ABC, approximation computation, which doesn't really need the likelihood, so essentially just uses some summary statistics of the data and checks whether the simulated summary statistics match, how close they are to the true statistics, and use that as a metric to perform inference. Very, very good. Another approach is synthetic likelihood, in which essentially, again, you generate data, you compute some summary statistics, and then you compute these, essentially, you compute a Gaussian approximation usually of these summary statistics, and use that to build an approximate likelihood. In this case, so you build a likelihood through this assumption of Gaussianity and of, only using the summary statistics of the data. These kind of are two families of models of, say, techniques. There are lots of other variants I'm not going to cover here. But another one which I'm going to focus today is inverse binomial sampling called IBS. And the good thing about this technique, which this is why I'm interested in it, is because actually there are no approximation involved. So you actually estimate the log likelihood of the entire data set with under some, say, requirements. And turns out this is actually a fairly old technique, say, published by Haldane in Biometric in 1945. Then there's been some work by Dehout in 1959, and then some other work in the 70s, and then it kind of disappeared until we kind of rediscovered it, I would say, independently. It's one of the cases in which essentially you find something, and then you check the literature, and say, oh, someone else already found it. But let's say what we did is with my collaborators, Bas van Opheusden and Luigi Acerbi. So it's we first of all, let's say, kind of rediscovered this technique, and then by say we realized that it's actually quite powerful to be used nowadays for simulator-based inference. So of course, let's say in 1945, people were not thinking of this technique as something for simulator-based inference. It was something, let's say, just like a relatively esoteric statistical technique, which we're not actually used in practice. But let's say nowadays we have the power, and it's actually to make good use of it. So that's what we kind of explored in our recent work. This preprint, which is under revision. And so just to give you the problem setup, so you suppose you have a data set with n data points, so whatever trials of an experiment, different, say, n observations. You have, so for each data point, so you can divide, you have some independent variables, which you call x. X1 can be a vector of whatever. In the experiment I mentioned before, x would be, for example, the orientation or the contrast of this patch, which is shown to this mouse. And you have some y's, which are dependent variables of observations, which are, for example, the responses in the brain, or even the physical response of a subject, the buttons, left or right, or whatever the responses in your experiment. And our goal again is to compute the log likelihood of this data set. We only care about the dependent variables, so we put on the right-hand side here, so the independent variables and the model parameters. And so we can actually write it explicitly. So what I'm writing here is just explicitly log likelihood. I'm just, there is no assumption here. I'm just essentially unpacking the log likelihood using the basic laws, probability. And in the simplest case, you can think of the sum, say, as essentially for each data point you have, what's the probability of observing, observation yn, given that in that data point or that trial, say xn was the independent variables. This is kind of the simplest possible case, but let's say, this our method work in the most general case. And we can just, rename this complicated thing as it's the log likelihood on the n data point. Okay, so we want to compute this. How do we do about it? So the point with IBS is actually that it's incredibly simple, and that's why I think I kind of like this approach. So there are some requirements, of course. First of all, we require that we can sample, say, fake observations or synthetic observations, given condition or everything happened before, or so everything else, let's say. So we can sample yn, given that we have, yn to 1 and -1, and also all the x's and the model parameters. So this is what we call, what we define in the paper as conditional simulation. Not all models allow conditional simulations. Many models do, some other don't. So it depends. Sometimes you can solve it. The other requirement, which is a bit less strict, is that yn is discrete. So it comes from a discrete set. If it's continuous, probably doesn't really matter. That there are lots of relatively cheap ways in which you can convert from continuous to discrete. I mean, the easiest way, of course, would be to discretize the data, but you can be a bit smarter about that. So I think it's not a major problem. One other thing I said, which matters, that you want for every data point that there is a non-negligible probability of the response, this observation, to be drawn, simulated from your model. And the reason why will be clear immediately. So the argument for IBS is just simple. For each data point, what you do is you sample from your model, and you keep sampling until the synthetic data points that you generated matches the true data that you have. Okay. You count how many times you sampled, and you call it K. And then the estimator of the log likelihood for that trial, the IBS estimator for that trial, is given by this, let's say this is a harmonic number, but minus the harmonic number. This is a truncated harmonic series, okay? And then you just simply sum up over all trials. And it's as simple as that. It can be proven, of course, that this is an, so it has very, very nice properties. I don't have time to actually go through derivation here, but you can look at the paper. So first of all, the IBS estimator is unbiased, which is actually really beautiful because, so let's say, so you know that, if you sample enough, you will get the exact number. Also, it's approximately normally distributed. And actually, this approximation is actually really, really good. So let's say you pretty much get a Gaussian estimator. One thing which might be surprising is that the variance for each trial is actually bounded, uniformly bounded. So let's say essentially it's actually, I think this pi squared divided by 6, but don't necessarily quote me on that. I need to double check. But still, let's say, so essentially, so it's bounded. So let's say, so you know that variance is not going to be crazy. So actually, you know, in a priori, it was going to be variance of your estimator at worst. And then, we can actually exploit Bayesian inference to come up immediately with an estimate of the variance for each estimate, which actually turns out to be very well calibrated, which we proved empirically. And if we pay attention to what we said, a few slides before, this is actually extremely convenient as an estimator because it plugs in incredibly well with GP regression. So the standard GP regression model used everywhere is that you have a function, in this case would be the log likelihood, plus some observation noise, which is Gaussian distributed. Okay, and this is exactly what we have here. And even the magic here is that we also know exactly what's the noise. I mean, almost as we can use this calibrated estimator to really plug in, what's the noise, what's the amount of noise, etc. So this works perfectly with the GP regression model. So now we can go back to the case, with the VPMC, but say now we can extend it to the case with noisy likelihood, which is we have log likelihood estimates which are actually not exact, but noisy. So again, so our goal is to extend the previous work by in the case in which we have noise in the evaluations. Noise could come, for example, from these log likelihood estimator I just mentioned, IBS, but it can come from anything else. So there are other estimators which don't necessarily have exactly the same properties as IBS. But they're kind of unbiased and kind of normally distributed, and then those would be fine. For example, you can use synthetic likelihood to do something like this as well. So it's not limited to IBS, you can use other estimators as well. And of course, you can wonder, well, okay, but why do we need to extend this work? So can't we just, use GPs, just tell the GPs that, the observation are noisy and get away with it and automatically have everything that we did so far work also in the case with noise? And if we do that, turns out it doesn't work. So what I'm showing here in each panel, it's a different model. So these are all models from computational neuroscience or cognitive science. The title tells you the kind of model, and when the model is repeated, it's because we applied to two different data sets just to check. And on the x-axis, we have the number of function evaluations, so the likelihood evaluation to do. And on the y-axis, we have a metric. In this case, is the marginal marginal total variation, which is, or mean marginal total variation, which tells you essentially how overlapping, well, actually, how non-overlapping are, let's say, or how distant are, say, the marginals of the posteriors from the true posterior. So essentially, you want this to be, ideally 0. So say in this case, perfect overlap of the posteriors, of the approximate posterior and the true posteriors. In practice, let's say, I put this arbitrary threshold at 0.2, which tells you essentially, ideally, for example, you would like to have the posterior which are at least, 80% overlap. It's arbitrary, maybe you want more, but let's say, just to say that anything which is probably above this threshold is probably not really usable in practice because you get really bad approximations. Anything which is, above probably, 0.4, 0.5 is a really bad approximation. And what we can see here is that, it kind of works, and these number of parameters. So kind of works in low dimension, not that well, and then just really fails, very horribly in a high, even for 5 dimension, 9 dimension. So this doesn't work. We can try and fix it with simple patches, and we get a bit better, but still doesn't work. So I say this is not something I would recommend people to use, right? So that's why we need something specifically thought to work with noisy problems. So some insight is why is this failing. So, by the way, I was taking questions. So let's say you stop me if there is any question. Nope. Okay. So, why is this failing? The reason is that the previous version of VPMC uses this. So, in order to pick new points, uses what's called an acquisition function, and you want to. So, the acquisition function in a VPMC what it does is maximize the point-wise reduction in uncertainty of the elbow. So what it does is, it just looks at single points that if you sample from, reduce the variance locally there, just exactly where you sample, and you also use the variance as a metric for uncertainty. But if you have already a noisy evaluations of the posterior, even if when you evaluate at some points, you will just maybe a tiny reduction in uncertainty, because due to noise, to the noise observations, you will still have noisy posterior even after you observe something. So what you want to use is more an acquisition function which is more global and robust. And it tells by evaluating your points, essentially it tells you something more about the global structure of the function, not just what happens locally. And luckily, people might be familiar to you, say Marco Jarvenpää, Gutmann, Veitari, and Martinen, just last year. They did this fantastic archive preprint, which is now published in Bayesian analysis. I proposed this integrated media interquantile range, or IMIQR, or IMIQR, which is an acquisition function studied for problems of GP regression, which again first of all comes from first principles, and the goal is to reduce the uncertainty of the posterior over the entire space. So it's integrated over the entire space and not just locally. So it's kind of a global acquisition function. And secondly, like a trick that they do is that instead of using the variance as a metric of uncertainty, they switch to robust statistics that they work well in practice. So let's say they use the interquantile range. Essentially, I took this work, which goes really well, and let's say we implemented here from VPMC. And thanks to VPMC, we also can we make some improvement in the sense that we can have a fast approximation to this acquisition function, which is actually relatively expensive, through variational inference again. Again, not many details, but now we can see the difference. And again, there are the two things I was showing you before. There are some other methods I'm testing, but what we care about is the black function, which is this DQR. This is a new acquisition function that we've been using. And now you can see that it performs, well, pretty much better than anything else, or very similar to this other function here, to this acquisition function. But still now we have a method that actually is able to achieve usable solutions. These are not, let's say, terrible. These are approximations which are in some cases very good, in some cases decent. And so now you have a method that actually usable with noise. And turns out, let's say, it's also quite fast. So what I'm showing here is the average cost per function evaluations. And you can see, this method, but it was, to be fair, the method I'm comparing against, were not necessarily developed with speed in mind. It was more like, kind of proof of concept. But so we can see that by doing these tricks and variational inference, we can be, one order of magnitude faster than other methods, or just like 3-4 times faster than other methods. And this implies that you're not necessarily constrained to use this method, the VPMC, only when your model is super expensive. But even if your model is mildly expensive, take maybe a second or so, it might be convenient actually to use this more than MCMC to get the posterior, at least to get a first approximate posterior. Then maybe you want to refine it later. This is available as a very user-friendly package. Unfortunately, now it's only a MATLAB toolbox, and of course, there's a Python version in the works, which means I need to find someone to work on that. But let's say for the moment, this is what I have, and there's a lot of documentation in it. I like people to have something that's readily usable. Okay, just to conclude. So now we can cross this thing. We have something that actually, so we don't require exact likelihoods. We can work also with the say simulator-based inference, or with noisy likelihoods obtained through simulation. There are still the other problems which I would like to tackle, as next steps. But I would like to be a bit more generic, more general than just the specific points. So I think the approach I'm interested in, besides the specifics of VPMC that I mentioned, is I want to make a case, for smart Bayesian inference. So let's say, I think we have the tools now and nowadays, to do Bayesian inference in a way which is not just, which can exploit the active sampling and the idea that we can build model approximations which allow us to get to a posterior approximation actually very fast. So let's say with only, let's say, hundreds of evaluations. And I think, let's say, there is a lot of interesting case usages here, and especially for, let's say, how to apply, modern machine learning, modern AI to Bayesian inference. And I think, let's say, this is nice because if you think Bayesian inference, let's say it's a microcosm, let's say, because, you have relatively well-defined problem, finding posterior, but it's also an incredibly complicated task. And it's kind of similar to the real world in many ways in that, you have models, but, these models might fail. They might have, let's say, edge cases which are weird. And, and your method needs to deal with all these, cases, not just, with the best smooth scenario, but say also with, more complicated and complex cases. And I think there's a lot there to be done, as a kind of gym, for developing intelligent and smart active systems. And as you might guess, everything I mentioned is kind of, I think, let's say, fits fairly well, is that they were related to several research programs within FCAI, agile probabilistic AI, Symmetrybased inference, and also interactive AI, in the sense that, well, I haven't really focused on that right now, but say several of the things, I've been working on is, Bayesian inference, say, from the point of view, say, how humans, perform Bayesian inference, how humans perform decision making, and I've been using these tools to fit and explore, or say, ask these questions. So let's say this would fit with several of these lines of research. I would love, I'm just starting here. Actually, here today is my starting day at the University of Helsinki. So I would love to, say, to get in touch with people and, to know what your research is about, what you're working on. And yeah, just always up for a chat. Want to acknowledge, say, my collaborators from the IBS work, Bas, who's now at Princeton, and Regima, who's at NYU. And to say my previous lab, which I just left, in particular, Alexandre Pouget, who essentially allowed me to do this side work, which had really nothing to do with what he was doing, and he was very supportive of this work. And thanks for the invitation, for the organizer, and you all for listening to me rambling for almost 40 minutes.
Okay, thank you for the very interesting talk. So is there any questions or discussion? Please go ahead. Yes, I think Teemu has a question or comment.
Yeah, buongiorno, Luigi. Good to see you. Thanks for the brilliant talk. I think there was a lot of stuff, but fortunately you gave the pointer, so we'll have to dive into the papers. I've got two questions. One is that since there's a lot of people working on graphical models, I think many of us are interested in how do you see the fit with this work and this approach to model selection in graphical models? Do you think this is? I'm basically concerned about is it fast enough? Because in graphical models we'd normally explore quite a large set of different models. So is it fast enough to do the comparison while we're searching for good high marginal likelihood model structures?
Yeah, that's a great question. And so the honest answer is that, to say, so far I've been dealing with so probabilistic graphical models are not exactly black box models, right? So you often are aware of a lot of structure of the model. When you might be searching the space of models, but say for each model you know a lot of structure because say you have the graphical model. And so in this sense, I would say it's an open question because there is not something I've been investigating so far because I've been focusing on the black box models in which really you're only given the model either as a black box log likelihood that you can sample or as a simulator. But let's say you have nothing else. So I would say what I can say is that, for example, if you cannot compute the likelihood, and so you use them as a simulator. So let's say you have these graphical models you can sample from, but for some reason you cannot compute the likelihood. Then actually, for example, IBS might be a relatively good fit because even it is a kind of structure, so it's able to work even in a very high dimensional space, somewhat surprisingly. I mean, I haven't done this work specifically, but my collaborator Bas has seen this in other projects. So that would be something interesting to study. But specifically for VPMC and its application to probabilistic graphical models, that's something to say. I would say it's an open research question. So I don't have a definite answer now.
Thanks. Yeah, I was particularly pleased with the IBS criterion seems amazingly elegant with the harmonic mean and all that. So I'll definitely be taking a look at that paper. It looks really fascinating. So if I may, there was another sort of high-level question, or more like not a technical question, because your field or your appointment is on human and artificial intelligence. So how do you see the link? Is our brain doing something like that? Is there a link, or what might that link be here? Are these algorithms in our brains?
Yes. Yeah. Thanks. Yeah. Perfect question. I was expecting it. And so first of all, what I presented here essentially is the more I would say hands-on machine learning stuff. So let's say it is not necessarily, doesn't cover the entirety of what I've been of my research. But I say, yeah, the question related to here is whether these algorithms are in the brain. So I would say I'm agnostic. So I would see them, and I would see, for example, GPs and active sampling as something that definitely is. I mean, let's say that's my hypothesis. Let's say that definitely happens in the brain, especially the active sampling, because there are so many models of the world that the brain could be using, and I don't believe that the brain is just kind of do completely dumb random search. So this might be guided search. And if you do a guided search, it means that you need to have some ways to do guided search. So you probably need to have some uncertainty, and you want to refine your model where you think something. So there must be some concept of uncertainty. There must be some concept of say likelihood, or say approximate likelihood that the brain is using. And so I'm not claiming that say the brain is doing exactly this. Actually, no, I can claim that I'm pretty sure the brain does not implement VPMC. Okay, so we can be clear about that. But what I see here is that, let's say, the general principles, I think they would apply. So, and that's something actually I'm interested in, and and the research that I've been doing and I plan to do actually goes in that direction of seeing whether we can see the signatures of active inference in the brain. So there's a lot of signatures of active sampling, let's say in the real world for animals, foraging and doing some sort of active sampling in the real world. But say what I'm interested here is that whether there is active sampling in the way in which the brain builds models. So that's the closest the approximation to what VPMC is doing, right? So it's not about sampling the world, but it's about sampling from the model and building approximation of the true model. So that's something, yes, I think brain might be doing. Of course, say is the brain using GPs? I mean, I see GPs as a model of what the brain might be doing. There are several work, let's say, using GPs to approximate, to model human decision making. Again, I don't think we should take them literally as the brain implements a GP, but let's say GPs are a good model for and relatively agnostic to allow us to model what's happening in the brain. And maybe maybe the implementation might be closer to a deep net in some way. But again, GPs allow us as researchers to have a cleaner model, and kind of get rid of the details and to see, okay, to explore how this thing could behave, which kind of signature of behavior you could get, if you had something, akin to a GP exploring the space of models. So yes, that's something definitely interesting to explore.
Thanks very much. I'm sorry if I took all the discussion time. Maybe others have burning questions too. But thanks.
Well, I had a quick question. Thanks for the interesting talk. So my question relates to how kind of the use of variational inference in this context, which is like in lots of variational inference applications, in a lot of cases, the posterior approximation is not that accurate, right? Or may not be as accurate. So, which is fine as long as I kind of understand or get to know via diagnostic that it didn't work well. So my question is, if I'm applying that to a new problem and I'm getting a joint posterior distribution of my parameters, is there any diagnostic in your method that can tell me how much I can trust this approximation?
Yeah, that's excellent. So So first of all, let's say one note. Let's say, as you know, let's say people have been working on diagnostic for VMC for MCMC for many years. So and it's still somewhat of an open question. And for variational inference, is a completely new, almost to say the diagnostic for variational inference, are relatively new. Like only a few years of work that people have been working on. So and then there's even shorter time. I've been working on VPMC. So yes, I've been thinking about diagnostics, and at the moment, let's say my recommendation for example, if you go on on the say usage recommendation on the website and on the toolbox. So I definitely recommend to run multiple multiple runs of the algorithm for separate starting points, as you would run multiple MCMC chains anyways, and compare the results. Like MCMC, you can also, so if you see that the results are compatible, you can combine. So as MCMC, you could combine different chains. You can actually combine different variational posteriors in a way which is not say done yet, but say it's possible to do. So that's one way. Of course, that doesn't tell you everything, because say it might be that say all solution converge to the same solution, which is still not representative of the posterior. So it could fail, let's say, into an interesting way, which is still bad, but says there are different modes and you just not find them. And that to be honest, there is not much of a solution that I can tell, because that's still an open problem for variational inference, even for MCMC. If there is a mode which is far away and you don't sample from, there is really no easy way to find out. The other thing, which is more typical of variational inference itself, and it's kind of compounded with the fact that we have another approximation, which is the GP approximation, is the fact that the variational inference tend to underestimate the details. For example, it's kind of very known problem of variational inference. And in this specific case, again, what you can do some checks essentially, to test whether you're somehow underestimating details. It is hard to do because the assumption here is that your log likelihood is expensive or noisy. So that makes this kind of diagnostic very hard. So with standard variational inference, you can, the assumption that you can generally sample from or can evaluate your true model very easily. So you can check if there are discrepancies, for example, details, and you can run diagnostics. I would say here it's harder, so that's, I would say, still an open problem. I mean, you can do that, but I'd say it's very expensive to do. So it's still an open problem.
Thank you.
Okay, I think we are running out of time, so I want to thank the speaker and also the audience, and we will again meet next week. So
just one thing.